Structures for pH3, NO2 with a -1 charge, and SiO2. All right, after Lewis structures, we started talking about molecular shape. To determine molecular shape, you need a proper Lewis structure, and then you will count the bonding groups, which is equal to the number of bonds, any type. So single, double, triple all count as a bonding group. Number of lone pairs, you just count directly from your molecule, but it's only the ones on the middle atom. We will look at the Lewis structures for each of these, which we've already drawn the Lewis structures for most of these, so I'm not going to go through that process again. But let's look at these Lewis structures and count up our bonding groups and our lone pairs. So we see here with pH3, bonding groups, there are 3 of them, so each of the single bonds. Lone pair, we do have a lone pair on the middle atom. So 3 bonding groups, 1 lone pair. If we go back and look at our table, we have 3 bonding groups and 1 lone pair, means that it is trigonal pyramidal. So pH3 is going to be trigonal pyramidal. If we look at SO3, we have again 3 bonding groups because the double bond and the 2 single bonds all add up to 3. Lone pairs, we actually have 0 because there's none on the middle atom. The ones on the outer atoms we don't care about. So again, if we go back to our table, 3 bonding groups, no lone pairs is going to be trigonal planar. So SO3 is trigonal planar. NO2, we have 2 bonding groups, and we only have 1 lone pair that counts, only 1 on the middle atom. So 2 bonding groups and 1 lone pair is bent. So NO2 is going to have a bent molecular shape. Again, pause your video, see if you can figure out the last 3, and come back and check your answers. 3, you've got linear, linear, and bent. This slide combines pretty much everything we've done so far. Fill in the table. You've got molecule, name, Lewis structure, and molecular shape. Again, work through these and come back and check your answers. For the answers to this table, go ahead and check yourself. Here is another summary practice. So we've got name the molecules, draw their Lewis structures, and determine their shape yet again. So again, go ahead and pause, come back and check your answers. Notice we've got things going across here. I started to run out of room. And there's your last 2 at the bottom. All right, next topic was polarity. And first we determined whether a bond is polar or nonpolar. The quick check here is if the 2 atoms are different, it will be polar. If the 2 atoms are the same, it will be nonpolar. And this is about how much the atoms want the electrons, which is based on electronegativity. So go back and review that topic. But number 1, we've got 2 different atoms, so this is going to be a polar bond. 2, again, 2 different atoms, so it's polar. 3, it's 2 nitrogens, so this will be nonpolar. Number 4, 2 different atoms makes it polar. Then we went on to talk about whether molecules are polar or nonpolar. And this is where you're going to need a Lewis structure in the correct shape. Here we're trying to visualize what the shape of the molecule looks like, and on the surface, whether the surface is the same all the way around or if it's different. So pH3 was trigonal pyramidal. We've already determined these shapes, so go back and double check those. But trigonal pyramidal looks like a pyramid. So that phosphorus is kind of up above the hydrogens. So that means on the surface, we have phosphorus on one side of the molecule, hydrogens on the other, so that's different ends. So this is going to be a polar molecule. HCN was linear. So here our ends are different. So hydrogen is different than nitrogen. So again, this is going to be polar. SiO2 was linear. This time the ends of our linear molecule are the same, so it's symmetrical, so this is nonpolar. Go ahead and pause and try the last three and come back and check your answers. Trigonal planar, all the way around the atoms are the same on the outside, so it's nonpolar. NO2 was bent, so the top half of the molecule is different than the bottom, so that makes it polar. H2S was also bent, so again, top different than bottom, which makes it polar. All right, determining molecular weight. Molecular weight is going to give us an idea of how big our molecule is. To determine molecular weight, you need to look at the the atomic weights on the periodic table for each element. Those are the decimals. So for example, carbon has 12.01 written underneath of it. That is the weight of a carbon atom. So we're going to add all of those together for the different elements in our molecules. I typically round to the nearest whole number unless it's right in the middle, something like chlorine, 35.5. So feel free to round your numbers as well. So nitrogen has an atomic weight of 14. Hydrogen has an atomic weight of 1, and there's 3 of them. So add that together and we have 17. The units for molecular weight are grams per mole. So this means if I have a mole of molecules, which is at 6.02 times 10 to the 23rd, it will weigh, in this case, 17 grams. SO3, sulfur has a molecular weight of 32. Oxygen is 16, and there's 3 of them. So if we add that together, to do this one in my head real quick, 48 plus 32, we have 80. And again, grams per mole. So try numbers 3 and 4 and come back and check your answers. 2, you've got 27 grams per mole for HCN and 34 grams per mole for CH3F. All right, molecular weight then helps us determine the strength of London forces. London forces is just the surface area interaction between two molecules. The bigger the molecule, the bigger the surface area, the stronger the interaction. So we're going to rank weakest number 1, strongest number 4. So really we're looking at size. So the weakest will be the smallest, so that is the NH3. The biggest will be the strongest, so that is SO3. Then if we look at our two middles, HCN would be number 2, CH3F would be number 3. The second intermolecular force we looked at was dipole forces, and dipole forces simply come down to whether or not the molecule is polar or nonpolar. If it's polar, it has dipole forces, so NH3 does. SO3 is nonpolar, so no dipole forces. HCN's polar, so we have dipole forces. And CH3 also has dipole forces. Hydrogen bonding, you need to have an HN, HO, or HF bond somewhere in your molecule. If you do, then you have hydrogen bonding. If you do not, then you do not. NH3 has a nitrogen-hydrogen bond. If we remember what our Lewis structure looks like. So that has hydrogen bonding. SO3, there's no hydrogen, so the automatic answer is no. HCN, we have hydrogen and nitrogen, but they're not attached to each other. Remember, this is what our Lewis structure looked like, so no hydrogen bonding. CH3F, hydrogen and fluorine, but the hydrogen is not attached to fluorine, so again, no hydrogen bonding. The only one in this case that has the hydrogen bonding is the NH3. So for ranking boiling points, we need to think about all 3 forces. The one that has the most forces is going to have the highest boiling point because it's more difficult to pull them away from each other. The one with the fewest the fewest intermolecular forces will be the lowest boiling point because it's easier to pull them apart. So London forces, everything had London forces, so yes. Dipole forces, we said yes to NH3, no to SO3, and then yes to the other 2. Hydrogen bonding, the only one that had it was the NH3. So If we transfer this to the next slide, fill this back in real quick. And now we're going to think about that boiling point. We're going to give the highest boiling point number 1, or excuse me, the lowest boiling point number 1, and the highest boiling point number 4. So the NH3 has all 3 forces, so that will be the highest, so that will be number 4. SO3 only has 1 force, the London forces, so that will be the lowest, number 1. Then HCN and H3F, we have a tie at 2 forces each. So this is going to be broken by molecular weights, which HCN was the 1 plus 12 plus 14, which was 17 grams per mole. CH3F, we have 12 plus 1 times 3 plus 19. So we've got the 34 grams per mole. So that means HCN is smaller. So that's going to be number 2. CH3F is a little bigger. So that is number 3. So that is how you rank your boiling points. Figure out your forces, tally them up. The one with the most forces is the highest boiling point. The one with the fewest forces is the lowest boiling point. Anything with a tie will be broken by size. Here's a couple examples where we're just looking at 2, and you need to figure out which is the key force that's the difference, and that will be the one that then determines the boiling point. So C6H12 versus C10H20. Anything that's a hydrocarbon, so just carbon and hydrogen in the formula, is always going to be nonpolar. And it also does not have hydrogen bonding. So the only thing that matters is the London forces and the size. NH3 versus PH3. NH3 has hydrogen bonding while PH3 does not. So that's the key difference. CO2 versus SO2. CO2 is nonpolar. CO2 is nonpolar. SO2 is polar. So it's dipole forces. That is the key difference. Here is another problem where you're going to work through, figure out all of your forces and rank boiling points. So go ahead and try this one on your own and come back and check your answers. CO has London forces and dipole forces. It does not have hydrogen bonding. H2S has London forces, dipole forces. It's a bent molecule, but no hydrogen bonding. NO2, London forces and dipole forces. CH4 only has London forces. It's a non-polar tetrahedral molecule. So the CH4 has the fewest forces, so it will have the lowest boiling point. The other 3 are all tied. They all have 2 forces. So we have to calculate our molecular weights. The smallest one was CO, so that's going to be number 2. The next biggest is H2S, so that's number 3. And our largest is NO2, so that is number 4. All right, here's a final table that has pretty much everything from the entire chapter built into it. So take some time and work through this. If you can fill out this table correctly, you've got a pretty good handle on chapter 7. So try your best and come back and check your answers. All right, here are your answers to your final slide. Do notice that I mixed up the name and Lewis structure columns. I'm sorry about that. Otherwise, everything should be there. Please let us know if you have any questions on chapter 7.